Steve Shannon, thank you so much. You're my first victim at North Carolina State.
I'm always a victim.
So, as we always like to do on the Titans of Nuclear podcast, we like to get to know our guests from the beginning, where their interest in science and technology and physics comes from. Where did it all begin with you?
Hard to say. I can't think of a time when I wasn't interested in it. I guess if I was going to point to anything in particular, I'd attribute it to my dad. He was an engineer when I was growing up, and
what kind of engineer?
He was an industrial engineer. Actually, he was always self-employed, so he was always starting his own companies. I think he's had like 3 or 4 companies in the time that I've been, and always small companies. Never kind of like everyone always kind of envisions starting up your own company now as the Silicon Valley startup model, but he was more of the traditional, just start a small company, mom and pop shop, and run it. So he did everything from industrial hygiene and running industrial labs that would do soil sampling and air sampling to selling industrial. He was a sales rep and would sell industrial equipment, chlorinators, air compressors, things like that to large industrial firms out in Detroit. So
always a lot of interesting stuff to talk about at the dinner table.
Yeah, well, it was one of those things where I learned 2 things I got from my dad. The first, which both came true, was the first one was that I had an interest in science, and the second thing was that he was always, since it was always a small company, he was always CEO/head custodial staff, because you do everything. Yeah. And ironically, and that was one thing I decidedly didn't want to do, which is why when I first graduated from college, I went to work for a big company.
Where did you go to school?
Michigan.
Yeah.
But as it turns out now that I'm a professor, I'm now CEO and head janitor, just like my dad is. It's just because you got to do a little bit of everything as a faculty member as well. But yeah, I went to Michigan. I'd grown up in Detroit. Having a school like Michigan in your backyard with in-state tuition, it's hard to pass up.
Especially a school like Michigan.
Well, it's a lot like NC State. It's got a great reputation, and I've always been a big fan of the big public in-state schools, because with the tuition still, with the cost of college the way it is nowadays, it's a real opportunity to not go too broke trying to get a college education, because it's not easy now. It wasn't easy when I was doing it, but I can't imagine how hard it is now to accomplish it.
Yeah, can we go off track for a second? I'd love to kind of hear your thoughts. Since you did it, I often think the same way as you. Because I went to state school as well, and I thought about finances, even back then, and how can I kind of best position myself later in life. Now that you're still in the university system, you've seen these costs just escalating like crazy. Like, what's going on there? Like, what are we going to do?
There's a few. I mean, there's depending on there's a few arguments people make for why the cost is going up. One of them is that if you look at, for example, percentage of state support for the state universities, those have been that has been in steady decline over the years. Also, college infrastructure has built up over the years. If you look at the number of administrative and staff positions that have been built up at universities over the years, that has grown in the past few decades. And so the combination of those 2 things, I mean, NC State's made a lot of, this is the one school I've been at, has made a lot of efforts to try to lean out the operational process and try to increase efficiencies institutionally. But this could be a whole podcast. I mean, you can go in 100 different directions with it. I think at the end of the day, it's like a college education is like any other investment. You put money in because you expect to get more out.
Yeah. And
if that continues to have a positive rate of return, then the cost of the investment justifies it. Your return will drop because the upfront investment is greater. But at the end of the day, I think that college education is still, even at the prices are at nowadays, is still worth every penny. But I'm biased. I've
part of the system.
Well, not as much I'm part of the system, but I've personally seen a lot of my personal benefit and just self-improvement going through the process. 8 years of college, I did a lot of growing up. It isn't just what you learn in the classroom, it's what you learn outside the classroom. And I think that I look back on the time I spent at Michigan, both undergrad and graduate school, and still probably point to it as some of the most accelerated learning that I got over the course of my entire life. So I would do it all over again, even at today's prices.
Yeah, awesome.
So
What did you get your PhD in?
so I got my PhD in nuclear engineering.
And was there a specific subset? I know you're the plasma guy now, right?
Mm-hmm. Yes.
So how does that relate to nuclear engineering? Is that a piece of it?
So traditionally, nuclear engineering or plasma science in the realm of nuclear engineering came from the fusion energy effort.
Yeah.
So as you know, traditional nuclear engineering, the whole idea is to control and harness energy from splitting atoms, and then the flip side of that is as you go to lighter nuclei, you can get a similar nuclear effect, but by joining two lighter atoms together, you can get a release of energy.
And where does that release of energy come from? I know that when you split an atom, there's almost like a lot of potential energy stored, because you got the strong force counteracting the electromagnetic force, and when you split an atom, you're able to break it free, and you get your two positive magnets that then shoot off and turns into kinetic energy. What's going the other way? What happens there?
As far as where the energy comes from?
Yeah. How do you get the extra energy out of fusion?
So the net origins of energy are the same. That whenever you combine protons and neutrons together, the mass of the collection is less than the mass of the individual particles, and that mass deficit is whenever you combine two atoms together, is going to be released as energy. Yeah. So it's similar to how it works whenever you're fissioning a heavier nucleus, is that it's kind of working in the opposite direction. The mass deficit is more beneficial whenever you take a nucleus and you break it in half. And so it's E equals mc squared. If you start with one mass and you go to say a lighter mass, then the net effect is going to be that the energy has to go somewhere. And if it's not being retained as mass, it's going to be released as kinetic energy. Yeah. So in the case of fusion, what happens is that you fuse particles, energy is released. The energy is released as kinetic energy, the particles that are formed in fusion. So for example, you'll produce helium and a neutron, for example, and so those two particles will take kinetic energy and fly off, just like when fission happens.
So when they fly off, then they start bouncing around with other particles, and that creates heat. That's the heat of particles bouncing around.
So plasma, so fusion energy actually leverages that heat for two reasons. The first one is the idea that the heat can be converted into electrical energy, similar to how you do it for a fission power plant. And the other half of that is that the heat can also be used to sustain the reaction, right? So unlike a fission process where you have a chain reaction where you're controlling, you're basically trying to you put a leash on your dog, so to speak. You're trying to control the reaction. In the case of fusion, you need to put energy into it to sustain it. Now the way your current fusion reactors work is you have to kick a certain amount of energy into those charged particles to get the fusion reaction to occur. Eventually, if you can get enough efficiency in your system, you're making more energy than you're putting in. And then the real holy grail for fusion is a kind of the burning plasma concept, where the energy produced by the fusion event, by accelerating those charged particles even further, will actually sustain the plasma reaction in the fusion reaction without the need for auxiliary heating. So those charged particles will stay in the fusion reactor, and actually, as they knock into other particles, will provide enough additional heat so that you can get carry-on fusion events to occur.
Wow. And what are those carry-on fusion events? Would those be different particles or the same fuels?
Nope. The whole idea is you'd still be driving it off of deuterium and tritium, or just deuterium. Those are the isotopes of hydrogen that will give you probably, I guess you could say, that the most energetically advantageous fusion reaction. The lighter the nuclei, the lighter the nuclei, a couple things happen. First of all, the lighter nuclei provide you with that energy bump by decreasing the mass of the total mass of what's being formed. But the other thing it does is that if you think about what you're trying to fight in the case of fusion, is that you have to heat these particles up enough. So you think about an atom. So one of the things I teach my class whenever I teach my introductory nuclear engineering classes is that if a nucleus, so we're sitting here at DHO Library, right? If the nucleus was the size of a tennis ball, the atom would be larger than NC State's campus. It would extend to the state capitol, Whole Foods, Centennial Campus, and close to PNC Arena.
It's just mostly empty space.
It's mostly empty space, right? But so,
you seem solid though. You're composed of atoms, and you seem fully solid.
well, I guess.
Just our eyes playing tricks on us.
I guess it's all relative. If you take the, if you were to take something that has the mass of the Earth, and you were to give the Earth the density of a neutron, so a single nucleon that makes up a nucleus. So you take the radius of a nucleus, you know the mass of a nucleus, so you can calculate a density. So if you said, okay, assuming that you had this much mass, the mass of the Earth, and you squished it into the density of a neutron, it would be about the size of that building, the four-story apartment building with a coffee shop on the bottom.
Oh my God.
So that gives you an idea of what the scaling of just how much of that mass is contained within those particles. I mean, the mass density, if you think about it in terms of just mass per unit volume, is amazing when you start talking about nuclei.
What is this though? Then when they talk about like this origin of the universe, and they say the whole universe could have fit in a marble or something. What's that then?
That's something I don't.
That's another level deeper.
That's another level.
Because inside of your neutron, it's also mostly empty space with respect to quarks, right? It's like you got that same principle again or something.
I believe so, and I say that when it comes to the origin of the universe and that everything's squeezing into something that big, that environment is governed by laws of physics that don't even apply to the fields we work in. Yeah. Nor has it been, it's not like we can reproduce it. All we can do is think profound thoughts about it, because to be able to produce that type of environment,
yeah.
And they're trying to. I was just at a DOE workshop, Department of Energy workshop, where they were talking about trying to, replicate that energy density and mass density, or at least get closer to it, so you could start studying how mass interacts on that level.
Wow.
Obviously they're not going to get close to like the Big Bang type densities, but just trying to. It's like every other endeavor. You're just trying to sneak up on some ideal, and they're trying to understand a little bit better.
So we were talking about fission and fusion, and your studies led you to study plasmas. Mm-hmm. So what happened there? Where did you take those studies?
So the fusion studies and the plasma studies. So the idea is, remember I said that you had to heat up the gas. You had to put a lot of kinetic energy in those particles to get them close enough together to get them to fuse. Yeah. And you're fighting that Coulombic repulsion. They're both positively charged.
Right.
And if you calculate how much kinetic energy you need to overcome that Coulomb repulsion, it's energy that if you were to just heat the gas up to that temperature, all the electrons are stripped off, and what you're left with is a completely ionized gas. The electrons are stripped off, you have positively charged ions, you have negatively charged electrons. And so now, unlike a natural room temperature gas like it's in this room right now, all of the particles have this long-range force, Coulombic force, where they can all interact with each other. So you have this collective behavior.
That's like the electromagnetic force.
Coulombic electrostatic type force. And then if the charge is moving, then you're producing. You can start producing electromagnetic waves, electrostatic waves in a plasma. But the basic idea of the difference between a gas and a plasma, fundamentally, is that a plasma will collectively respond. Right. In fact, that's how one of the stories with plasmas is that's how plasmas originally got its name. So when I first went into plasmas, I went home for Thanksgiving and I told my mom, I said, I'm going into plasmas. And she's like blood? That's what she observed. Everyone always thinks it's biology, because most people, when they think of plasmas, they think of blood plasma.
Yeah.
Right. And it turns out that actually the naming it has a history there. Originally, plasmas were referred to as radiant matter because it was a gas that glowed, so it was radiant. And then they determined that it was ionized gas, and so they started to refer to it as ionized gas.
And the ionized gas just means that the electrons are somewhere else?
It means that you've torn the electrons off the atom and produced positively charged ions and electrons. So it's the process of ionization is the separation of that charge from the nucleus, right? And then one of the pioneers in plasmas, I believe it was Irving Langmuir, who actually lived in upstate New York. was studying plasmas, and he was sticking little metal probes into an ionized gas. And he noticed that whenever he'd apply a voltage, the entire gas would move around. Where it glowed would kind of slosh around, like, almost like you were poking a living thing with a stick. But it was collectively responding, right? And he made the comment that it almost looked like under a microscope, a living cell responding to external stimulus. That the living cell was that the plasma in the cell was actually moving around. And so he started to refer to the gas as the plasma, because that was what the inside of the cell, the fluid inside the cell was referred to.
Wow.
And so actually that's where it got its name, was in comparison to how the plasma responded to external stimulus and how a living biological system responds to external stimulus.
Brilliant.
So there actually is a similarity there. Now, this collective behavior is one of the things that defines a plasma. And what this is, one of the things that you can really take advantage of in a plasma is the fact that it's made up of charged particles. So, for example, because of the mass difference, so there's two things. So let me jump to the end and then I'll explain.
Yeah.
After grad school, I went to work. I started to use plasmas to manufacture computer chips. The idea was that I would use the electrons and ions that were produced in a plasma to modify the silicon or the silicon dioxide or the aluminum or copper or whatever else was being used to make a computer chip.
And this was like to dope it in a specific manner?
So doping uses ion implantation, which is still using charged particles and charged ions, but isn't leveraging the collective behavior of the plasma to accomplish that goal. It's more of a ballistic. We're going to take an ion, we're going to charge it, we're going to ram it through an electric field and then slam it into a surface. Okay. What plasmas do two things for computer chip manufacturing. You need a chemical reaction and you need directionality, right? So what happens on a plasma is that at the boundary of a plasma, you get something called a sheath. And what a sheath does is it'll accelerate the ions, the positively charged particles, it'll accelerate them down perpendicular to the surface. And so what it does is it just heats up. So if you're looking at this table, for example, it would just heat up the horizontal surfaces, but if I had vertical surfaces, like on the side of the table, none of the ions are hitting this part. So what I do is I heat up this part, just a few monolayers of atoms, but I don't heat up the vertical part.
And this gives you a very consistent manufacturing process.
It gives you the ability to control the direction in which a chemical reaction occurs. Chemical reactions are going to be driven by the temperature of the surface.
And what chemical, so you're pre-configuring your material, your substrate to already have all it has the mixture of elements in it that when it gets to a certain temperature, it catalyzes a specific chemical reaction. So you pre-mix it up and then you apply the heat and it does something.
So here's what. So the heat is one part of the equation the plasma gives you. That ion bombardment, we call it. The other part of what a plasma gives you is that since you have so much of a mass difference between the electrons and the ions, depending on how you heat the plasma, you can actually preferentially just heat up the electrons and leave the ions and the neutral gas particles that are in that system at roughly room temperature. Okay. So to explain the benefit of this, silicon growth, solar cells.
Yes.
So thin film solar cells are fabricated using with amorphous silicon or polycrystalline silicon, and the way they do it is they take a gas called silane. It's SiH4, and what they used to do is they would heat it up with a hot filament. And they would heat it up to the temperature that the molecule would decompose. And then you'd get the silicon off of the molecule and it would attach itself to glass and you could grow solar panels on glass. And that was how the original solar panels were made. That's how original flat panel displays were made, was depositing amorphous silicon on glass.
Okay. Because you got to remove the silicon from the oxygen that it starts off with.
The hydrogen.
Oh, the hydrogen. Oh, right.
Right.
So So you've already gotten, because silicon starts off as sand, silicon dioxide. So you've already removed
all that.
Oxygen.
And so
now
what
you just got the H's.
Now all you got is and the benefit of silane SiH4 is that it's a gas.
Right.
So it's easy to deliver into a chamber right. Now, the problem is that the temperature you have to heat silane up to get it to decompose is pretty high. So that limits the kind of material you can deposit amorphous silicon on.
Right.
But if I could instead take a bunch of electrons and heat those up, I can give electrons sufficient energy to break molecular bonds without heating up the gas itself. All I'm heating up is the electrons. And the electrons have such little mass that that I can actually, there's atmospheric plasmas where I can expose myself to electrons that have a thermal temperature of say 50,000 Kelvin, but they're electrons, so they're not going to do anything. If the gas was 50,000 Kelvin, I'd be in big trouble.
Right, because its effect on other material is a function not only of the temperature, which describes the speed of how the molecules are moving, but also the mass of those molecules, or the mass of the part of the molecules. Right. So the electrons have orders of magnitude less mass than your neutrons and your protons, and so if their temperature is high, it doesn't impart a lot of energy onto
a heavier material. But now what it can do is if I have a chemical bond, those chemical bonds are still made up from electrons. So if an electron interacts with a molecule, it can smack into those electrons and break chemical bonds. Yeah. And so now instead of thermally heating up silane, for example, to make silicon and hydrogen, I can have an electron come in and hit that molecule, break it up.
And then the hydrogen goes up and the silicon goes down.
Well, the hydrogen diffuses off because it's still a gas. The silicon will eventually fix itself on the surface.
Yeah.
Some of the hydrogen will too. That's a whole different story. But the idea is I can still decompose the molecule.
Yeah.
But now I'm doing it at room temperature.
And does plasmas only work with gases?
So plasmas are the natural progression of heating up an element. So you go from solid. If I heat up a solid, it'll turn into a liquid because I've broken those atomic bonds that produce a lattice structure.
And how do you give your silane enough energy to make it a plasma? How do you impart that energy on it?
With the free electrons. So what'll happen is that if
you create some sort of a field, you just create a field around it, or
so normally what'll happen is I'll have a volume of gas.
Yeah.
And the way you do it in industry, or for man-made plasma, is you apply an electromagnetic field or an electrostatic field. So in the case of computer chip manufacturing or for silane, they'll apply a field that's in the radio frequency range. So typically around tens or hundreds of megahertz. Actually, it sits right in the radio band for I think it's shortwave radio. And there's frequency bands in the radio spectrum that are licensed for industrial use. So if you go in my lab, most of my generators are licensed with the FCC, because if I were to use them in a way that I wasn't shielding their output, I would be broadcasting.
And you have to go through the FCC even if you're developing radio waves just in your own building? If you're saying, listen, not inside my building, you can't do whatever you want? Spectrum? So
I can't. I shouldn't broadcast it.
Okay.
So there are specific frequencies that are used for industrial applications, and the idea is that as long as I'm doing my experiments in a Faraday cage, as long as I'm not radiating the RF,
they're cool with it.
I'm fine. Yeah. I'm not going to interfere with the radio spectrum and with any sort of broadcast.
Yeah.
But if I were to broadcast it, if I hooked my generator up to some crazy antenna that just blasted, right? Then if I happen to be blasting, 88.3 or 87.1 or whatever the frequency is. No more NC State radio. Yeah. I have generators that have more power output than NC State's radio station.
Really? Oh,
just at different frequencies. But I also have
through these radio waves that you're able to create the electromagnetic field that is perfectly tuned in order to create the plasma for your silane. You can deposit silane or deposit your silicon on a substrate. Mm-hmm. Boom.
That's how it works.
Nice.
So you break up the molecules. But now that I've been using electrons instead of thermal heat, the gas is still at room temperature. So now I can start exploring things like depositing amorphous silicon on things like plastic. Mm-hmm. Now, thermally, if I was going to use that thermal heat up the silane to get that to happen, I'd melt the plastic. I could never do that with a thermal process. But with a plasma, I can do it at low temperature. And now I can deposit amorphous silicon on pretty much anything I want.
So then how come we don't have roll-up solar panels?
You do.
Okay. Ooh.
Those are commercially available. You can buy those. You can buy flexible solar panels. Flexible electronics is a big thing now.
Right, like on the new phones, they're foldable. So that's probably how they do this. Yeah. Super cool.
So that's how you transition from something like glass to, for example, a lot of the cell phone manufacturers will build their displays on plastic. They wouldn't be able to do that without plasma process, because you wouldn't be able to put down the semiconducting material for the devices on anything on plastic without melting it unless you had a plasma process.
Right.
So this was the direction I took plasmas in when I graduated from Michigan.
Wow. Practical industrial application for plasmas. That's awesome.
There's tons of this is the thing. This is the thing that's interesting is there are tons of practical industrial applications of
I thought all
plasmas.
of the fusion guys were just dreamers. No, real industrial application
No,
for
I
plasma.
mean, plasmas are funny. Even in the fusion effort's kind of funny because they always kind of you can make the NASA, the landing on the moon argument. There was no, people would argue there was no practical economic benefit to landing on the moon, right? We flew to the moon, we brought back a bunch of rocks, planted a flag, had a bunch of great movies that came out. But other than the revenue generated by those movies, not a whole lot of money was made by going to the moon. But then when you look at all the other technology that going to the moon advanced, right? The advances in computation, the advances in rocket engines,
Materials.
the advances in materials, that all of these things, there's a lot of things that we take for granted now that you can go and you can point back to its development as part of the moon effort that have had a tremendous effect on the economy. So fusion's the same way. Yeah. You take laser technology or optic or high quality optics that they use for the National Ignition Facility in California, where they're doing the 194 laser bombardment of a single pellet.
Yeah.
And you look at the technology development for high power lasers, for the pulse electronics that go into firing the lasers, for the optics that are used to focusing it down. All of that has had a kind of a more of a broader benefit to the scientific community because all that technology has found its way into non-fusion applications.
Yeah.
So even though the net application that a lot of the fusion people point to is still kind of dreamy, a lot of the technology they develop and a lot of the learning that comes out of that effort finds its way into things like computer chips. If it weren't for the fusion effort, we'd still have. So if you look at when plasmas were cut into computer chip manufacturing, it was around the mid-90s, maybe 1993, 1994 is when it was very first starting to get used. So think of the computing power you had back then.
Yeah.
You had cathode ray tubes, so you didn't have flat panel displays. Your computer processor was being clocked at like maybe 2-3 megahertz. Forget gigahertz. You were a factor of 1,000 slower in your clock speed. Memory was measured in kilobytes and megabytes. Yeah. And it was the scaling, it was the ability to control a chemical reaction so that those ions are only heating the surface. So the chemical reaction is only happening on this surface and not the vertical surface. Yeah. That I could fabricate devices down into the silicon and not spreading out where they take up more space. Yeah. So I could put in more computer chips, smaller, faster computer chips, and accelerate the development of electronics. 1994, a lot of the scale down and the ability to make more complex microcircuits came from the incorporation of plasma technology into computer chip manufacturing. It's used in almost 25% of all the individual steps that go to make a computer chip. If that plasma technology, if the fusion dreamers never played around with plasmas, we wouldn't have laptops, we wouldn't have iPads or phones. Cell phones wouldn't exist. Right. All of this stuff there wouldn't be a solution to this problem.
It's pretty amazing. I often advocate for these kind of big basic science research programs. Mm-hmm. I just imagine a world kind of like with ITER, right? So ITER, big collaboration for fusion. I don't think anybody's really going to come up with ITER from an energy perspective, but from a science perspective, and also from getting all these brilliant minds from around the world to work on a common problem together. Sure. I just wish don't you wish that we just took half the money that we spent on wars and set up these international science centers around the world where we brought science ambassadors essentially from every country working on these kind of problems, and the products that would fall out of it, even if they never solved the original challenge.
Well, I think you'd have to be some form of horrible person if you saw the advance of more efficient ways of killing people as being something better than.
So why do we do it? We could spend half the money that we spend on military. We could on basic science research and set up these outposts around the world instead of military bases that are scientific outposts. We could do that.
You could
generate a lot of goodwill.
the human race has had millennia of demonstration of lack of goodwill in that regard. I mean, it isn't like that modern society invented the concept of war and killing. So we have a long-standing history of misguided priorities.
Do you think we're bound to this current state of doing things, or do you think like with the right leadership, with the right kind of inspiration? I don't even mean political leadership. I just mean like the right type, like the original explorers, like the next Christopher Columbus. These types of people could change the way that we think about these priorities.
I mean, there's historically there's been lots of examples of people who have caused global where civilization philosophy has had. You've seen these dramatic changes because of one person bringing a new way of looking at things to the table. I'd like to think that we haven't run out of those people yet. But if I knew what that idea was, then I'd probably be doing something else right now, like trying to change the philosophy of Western civilization, which I wish I had ideas like that, but I unfortunately am not anywhere close to being there.
So how did you come back into academia?
Pardon?
How did you come back into academia? What prompted the change from industry back to academia?
So whenever I graduated from Michigan, I went out to Silicon Valley and started working for Applied Materials, which is a company that makes the manufacturing equipment that makes computer chips. So they were making the plasma reactors that the silicon would go in for manufacturing. When I first started there, I didn't have that much of I like when you start any other job, your schedule is pretty light. You're doing some training, but they're not giving you a lot of mission critical assignments because you just got out of school. So you're still learning the ropes. So I picked up a job teaching night classes at San Jose State in their chemical and materials engineering department. So I taught introduction to material science. I taught introduction to computer chip fabrication, ion beam interaction with materials, some graduate classes, some undergraduate classes, and just started to really like it. And I was very fortunate that the company I worked for was actually very supportive of me continuing to do that even when I got busy. And there was two reasons for that. First of all, they saw that this was, kind of energizing my own work because I was having to. I was taking a slightly different approach to problems than because I was still kind of at least a little bit tied into that kind of academic way of thinking. But on a more practical level, my company loved the idea of me having a 15-week window where I could basically recruit the brightest minds out of San Jose State and have them come work at Applied Materials. We hired 4 or 5 of the students who went through my classes. Yeah, amazing recruiting tool. It was great because it would be, the students would come and talk to me, and they just aced my class, and they knew I worked in industry, and they would ask about opportunities, and I just said, give me your resume. Yeah. And the ones that we hired were amazingly high performing. Yeah. And it worked out great. And so they were like, you just keep doing that. Yeah. But eventually I just kind of enjoyed the teaching part more and started looking for academic jobs. Yeah. And eventually landed at NC State. Yeah. And so what was it like moving out to the East Coast now? Well, I grew up in Detroit. Okay. So I grew up in the Midwest, went to the West Coast, and then came out to the East Coast. All so I've gotten flavors of the U.S. Gotten to see all flavors, and I'll say that I've enjoyed every place I've been. I grew up in Detroit, so Detroit will always be home. But I also haven't lived in Detroit now for 22 years, so it might always be home. But North Carolina will probably be where I hang my hat the rest of my life. Yeah. So. And your students, so you're teaching them nuclear engineering, mm-hmm. right? But what are you teaching them? Like, what are you really teaching them? What do you want them to come away with? So the conversation I always have with my graduate students in particular is that I really want, everything's built around them being, I want them to be able to work independently, right? Whenever I have grad students join my group, the first year is them coming to me and waiting for me to tell them what to do. And the goal is that by the time they leave, they should be coming to my office and showing me what they did and why they did it, and here's the results, and here's what we did, here's what we need to do next. When they get to that point, that's when that's when I feel like, regardless of the technology that they're working on for the PhD and the science they're developing aside, when they get to that point where they're able to advance the state of the art, and they're doing a big chunk of it without me telling them what to do next, just kind of giving them we should go look at this, and then they figure out how to do it. Yeah. That's the goal. That's what makes a good researcher. Yeah. Is finding your own path, finding your own novel way of doing things, and having the confidence to go and try it out yourself. I mean, I always tell my students, being an experimentalist is you got to really find the perfect balance between, cowboy and nun. Because if you're too much of a nun, you're going to be, and not disparaging the nuns, my aunt's a nun. But they tend to be a little bit more conservative in their thinking. They tend not to be the ones who take chances. And if you do that, you're never going to discover anything. But if you go full cowboy, you're going to break everything in the lab, and you're not going to learn anything either. And so you got to find that balance. And my students usually come in as one or the other. Either they are scared to death to touch anything, or they are just ready to void every warranty I have in my lab. And you find the common ground, and by doing that, you make them just extraordinarily productive scientists, I think.
Okay, so as we wrap up here, what is the focus of your lab, and what do you expect to come out of what your students are learning and the experiments, and where they're going to take this 10, 15 years from now?
So the area of plasmas for industrial applications there's still a lot of things about the plasma environment or the plasma state of matter that are not very well understood. If you think about how a plasma works, the idea that you have this multi-body system where every single particle is interacting with every other particle, if you want to model it exactly, you have full correlation where every single particle is interacting with every other particle. Now, up until now, we've ignored that, and we've treated the plasma as fluids, right? And we've used basic governing fluid equations with some electromagnetics thrown in to capture most of what we know about plasmas. There's still a lot to learn and to grow that model, especially as we start to get into new areas that plasmas have gone into. We talked a lot about material processing and electronics manufacturing, but plasma sources are starting to find their way into agriculture, medicine. They're using plasma sources to treat cancer. It turns out that if you take room air and you ignite it in a plasma, you produce the same chemical makeup that is generated by cells under stress. So you think about, when cells are under stress, they'll release a chemical, basically, what do you call it? It's a chemical marker that triggers the rest of a biological system that stress is happening. And this is how biological systems respond to things like viruses or just stress in general. So plasmas can produce that same thing. And what that allows you to do now is that you can accelerate the body's response to stress, and you can get it to handle the stress, whether it's a tumor or it's a lesion, a cut. You can get blood to clot by exposing it to a plasma source. You can accelerate wound healing, for example. So all of these new areas take plasmas into a process regime with regard to gas composition, gas pressure, how you heat the gas, and things like that. That's still relatively unexplored. And to get the understanding of how plasma works in that regime to the point that it's as well understood as the regime where you're making computer chips and nanostructures and atomic scale things, when you can get the understanding here to that level, you can start to do things equally extraordinary for like I said, for medicine, for agriculture, for a wide array of new applications that would benefit society immensely. So what's going to come out of my lab isn't going to be the philosophy that changes Western civilization, probably, but what we'd like to see is that what comes out of our lab is a technology that makes us maybe a little less paranoid to do stupid things as a society. I mean, if everyone's well-fed and everybody's healthy and all of this is, you increase the access of all these things to all people, suddenly you don't have anything else, you don't have anything to fight over, and maybe that's the way you maybe that's one direction you take in trying to solve a lot of the world's problems we were talking about earlier.
Steve Shannon, thank you so much.
Thanks, man.